Hi, welcome back. So we are in chapter 6, prediction by RCC at the outline prediction by classification to further explore a new framework concerning the concept of deep learning. And the name of this framework is known as the recurrent neural network, or the RNN. Basically, it relies on the concept of a sequence of series of events to occur. If you would have to read page by page from a book, logically important that you are in the current page, you have actually to understand what had happened previously. So perhaps that both information can lead you to some idea what the next page would be about. The concept, I think, of this framework, basically, it's not going to be too much complicated for you to catch up if you really have followed so far. I have decided actually to bring this framework with a simple example, and maybe we can just look at the idea behind it. If we would have like a kind of a series data set, series, what I mean, there's a sequence of series, maybe a time series, a movie, frames, whatsoever. So you could have like frame 1, frame 2, all the way to a number of frames. Previously, we have seen this concept of frames maybe as an episode. That episode have number of actions or transactions, or etc. that we discussed earlier. Maybe this series data could be related to date. Actually, the data set I brought even is a time series, like a weather condition. This is the data set we're going to work on anyway. We are recording the temperature of that weather at each day. So if we try to actually create a frame, number of days of temperature, maybe 4 or 5 days altogether, maybe we can choose 3 days for now. So each 3 days, we consider it as an input. Next, what we're going to do, take these 3 inputs, pass them into some kind of operation, which is the actual framework of RNN, and try to predict what is the 4th day temperature is. The 4th day temperature, it is actually the first input for the other 3. And the outcome of this, we're trying to predict what is the 7 days temperature like. And the 7 days temperature is the first entry of the next 3, and so on and so forth. I hope you get the idea. And since we have an input, we can do anything with it, right? We can follow any strategy that we like. And actually, there is one strategy what we've learned in neural network by creating hidden layers. This is my input. It's just a 3-knot hidden network, say of 5. And basically, we could do the exact same operation. So maybe we can create another one. We can just output one output out of this operation. We have worked over all this before, and the same concept is going to happen right now. So I hope you still remember. But the only difference here, as we said before, what we want actually, we want to keep track of what was happening before. In this case, what we're going to do, let's start with the first layer actually. The first layer, so I took my input to be multiplied by, let's say, some alpha input, whatever comes from here, added to whatever previous output, if there's a previous output at all. The outcome of this, we do some activation on it. And after we finish this, multiply the outcome of this by alpha output plus bias. This only happens in the case of the first input. Now, obviously why I did this, because the value of this is 0. There is no previous operation at all. That's why I kept all this together. Let's take the second input. We're going to take this I2, okay, multiply it again by the same alpha I. And again, as we said, we're going to add it to the previous output. This is the previous output. Let's call it S1. That was the entry of the first input by alpha I plus 0, because here we basically have 0, nothing before. We activate it, and this is S1. Now, basically, what we are saying, we took I2 multiplied by alpha I plus S1. And now we see what is S1, this guy here. Now, this S1, we're going to multiply it by another alpha. We call it alpha hidden, for example. So here we have an alpha I. So far, we've come to learn alpha output and alpha hidden, plus bias hidden as well. And once again, we're going to take this guy and activate it. This is my S2. Let's call it an S2. And whatever happens in S2, we're going to actually multiply it again, as we said, by the alpha output plus some bias output. Now, do not forget the operation of this S1 alpha 0 plus bias That is my first prediction. So this is P1. I predict that this fourth day is going to be this. This is my second prediction. That means I predict the seventh is going to be like this temperature. And you keep doing this again and again and again. Now, this concept is the entire forward application of that. We're looking at alpha I, alpha for input. We are looking for alpha hidden and bias hidden. And we are looking for alpha output and bias output. Now, first of all, let's define what is the input like. Now, we decided here 3, right? It's a size 1 by 3. The first day, second day, and the third. Every 3 days is 1 input. We need to multiply this, as we said, by some alpha input. So what's the dimension of alpha I have to be? This is going to be 3 because we need to meet up with the dimensionality here. Now, what is the second dimension of this alpha I? Be decided depends on the hidden layer. So let's say 5. As we said here, so this is going to be 5. So the outcome of this alpha I input is nothing but is going to be 1 by 5. This is going to multiply by alpha hidden. And the question is, what is the size of alpha hidden? Absolutely, we know that the alpha hidden has to be 5 here to match the dimensionality. But what is in here, once again, the answer is clear, depends on what is next. Hidden layer of 5, it is fine, you can decide whatever you want. So this is going to be 5 by 5. So the outcome of this, 1 by 5. My hidden bias, this guy here, is 1 by 5. It must match the same size. We said we're going to take this guy, whatever it is, which is this operation here, this is 1 by 5, and multiply it by alpha output. So this is going to be multiplied by alpha output. So let's look what alpha output looks like. In this case, it's going to be absolutely 5 here to match the dimensionality. Well, once again, we need only 1 output to be predicted. In this case, this is going to be 1. So the outcome of this operation, it is going to be as obviously 1 by 1, which is our prediction. And of course, the bias output, which is this guy here, it has to be the same size of 1 by 1. This is the entire operation of forward prediction, because this is what we want to do next, is back propagate as we did in neural network. We have to update this list of alpha input, alpha hiddens, bias hiddens, alpha output, bias output, and so on. The only problem here, it's not problem, the complexity comes when you take the derivative, this linking mechanism. So what I want to do, actually, I would like to take this now back propagate. So what my actually S1 looks like, let me write it down here step by step and see how we can take actually the derivative then. We call this is S1. And let's look at S2, and of course multiply by alpha output plus the bias output. Great. Let's continue now the S3 and multiply by alpha output plus the bias output. I'm going to start with the last one because the last prediction actually depends on the previous 2 predictions in this case. So if I want to break down this S3 wide open, what that looks like. The outcome of all this is a single number. I mean, this is y hat. And if I subtract this from my y, which is the actual, then I'll get the error term. And I have to multiply it now. Let's start taking the derivative. I will take one of them and the concept sustain afterwards. Maybe we can start with the alpha output just to show you the backward. But believe me, it's the same. By the way, you have to take into consideration the activation had happened here. Let's look here actually. That this x1 alpha I plus 0, this term here, it is my S1. And this term here is my S2. Where are the alpha output happens here? Well, it happens here only one time. So if I take this error, the derivative of this, it's going to be the outcome of this entire value. It's the combination of this S1 and S2 altogether. Input of x3 alpha I plus S2 plus S1. That's it. This is actually the derivative of alpha output. The same concept we're going to do actually concerning the bias output, the alpha input, the also alpha hidden and bias hidden. Last but not least, let's actually go to Python and implement this by simple example, and we see what's going to happen. So basically you got like day 1, day 2, day 3, and so on, and the sequence are quite obvious. So our strategy is we're going to take every 3 days and create like an input. This is our input. It's going to be 1 by 3, as you could see here. Next, we're going to follow the exact same strategy what we did by creating the input weight, hidden bias as well, output weights and output biases as well. So basically, we're going to look at the exact same dimensionality as I mentioned in the previous example here. I will follow the exact same dimensionality as I've been doing. These are 6,000 days, and I want to chop these 6,000 days into 333 because we need the input to be 3. And if you do that, it's gonna end up with 2,000 cases. I mean, input space, if you could say. Each one of them is 1 by 3. Looks like this. So we have the first input, the second input, third input, and so on. So there are 2,000 of them. And then I'm gonna implement here just the labels that we can use later on to look at the actual error. And the label here, you're going to be quite careful. So the first 3, as we said, is going to predict actually the 4th day, which is going to be 53. And these 3 is going to predict 52. And these 3 is going to predict next and next. Now, this is the entire forward implementation. It's obvious this is our prediction based on complete random weights and biases, but these are the actual values. So we're quite way off. Now we need to make the back propagation the exact same examples we said. So basically we have to look at the output gradients, alpha gradients, output bias gradients, hidden and bias gradients, and finally the input gradients. So this are now my new input weight gradients. Now I did the same exact thing again by forwarding them. It's just only 1 epo, by the way. I did not do any fancy things for 1,000 epo to keep doing this again. But the concept is there. This is the framework of RNN. I think we have reached to the almost the end of everything you need to know about case of classification. Maybe the last steps that you have to understand later on is a feature engineering. It's a very, very important topic, I think, to understand that when you get your data, how to make some feature engineering on it. But we're going to do that after we finish the last part of our map, and that is clustering. That's exactly what we're going to do next. I will see you then.